Welcome back. Before we begin, if you're listening tonight, feel free to share in the comments what you're curious about lately, a part of the universe you'd like to learn with, or simply rest with. Tonight, we're exploring a question that feels simple when spoken aloud, but becomes quietly profound the longer it's held in the mind. Does space ever end? It's the kind of question that doesn't demand an answer right away. It doesn't rush. It simply opens. People have been asking this for as long as they've looked upward. From early sky watchers mapping stars by hand to modern scientists studying signals that have traveled billions of years before reaching us. If this question has ever crossed your mind, especially late at night, you're not alone. If you'd like, you can share in the comments when you first remember wondering about the size of the universe. Many people trace it back to a childhood moment, others to a quiet night much later in life. There's no need to hold on to that memory. Just let it sit gently in the background as we begin. When we ask whether space ends, we're not asking whether there's a physical wall somewhere far away, not a boundary you could approach or touch. Instead, we're asking something far more subtle. Is there a limit to the universe itself? Or is our sense of ending something shaped by human scale and experience? To begin answering that, we first need to slow the question down, because space, in physics, is not quite what it feels like in everyday life. Most of us imagine space as emptiness, a vast, dark container where galaxies float like dust motes in a beam of light. But modern science describes space as part of something deeper, a structure, a fabric, a framework that combines space and time into a single connected system known as space-time. This fabric isn't still, it isn't rigid, it can stretch, it can curve, and under the influence of mass and energy, it changes shape. So when we ask whether space ever ends, we're really asking whether this fabric has boundaries, or whether it extends in ways that don't translate easily into human intuition. Already, the question begins to soften. There may be no edge to fall from, no cosmic border to reach, only structure, geometry, and scales so large that they naturally slow the mind when we try to grasp them. In the next chunk, we'll take this idea one step further by looking at what scientists mean when they talk about the observable universe and why the limits of what we can see are not the same as the limits of what exists. To understand whether space ever ends, we need to separate two ideas that often feel like the same thing: what exists and what we can see. In everyday life, those two usually overlap. If something exists nearby, we can look at it. If it's far away, we can walk closer. But on cosmic scales, this breaks down completely. The universe does not reveal itself all at once. It reveals itself at the speed of light. Light, despite how fast it seems, has a finite speed. It moves quickly, about 300,000 kilometers per second. But even that speed is small compared to the size of the universe. Because of this, looking far into space is also looking far into the past. When astronomers observe the sun, they see it as it was a little over 8 minutes ago. When they observe the nearest star beyond the sun, they see it as it was more than 4 years ago. And when they observe distant galaxies, they are seeing light that began its journey billions of years ago, long before Earth existed in its current form. This leads to a quiet but powerful idea. There is a limit to how far we can see, not because the universe stops there, but because light hasn't had enough time to reach us yet. This boundary is known as the observable universe. It forms a sphere around us, with Earth appearing to sit at the center. But this is not because Earth holds a special position. Any observer, anywhere in the universe, would see themselves at the center of their own observable sphere. It's not a map of everything that exists. It's a map of everything that has had enough time to be seen. The observable universe has a measurable size, about 93 billion light years across. That number alone can feel abstract. A light year is not a measure of time. It's a measure of distance. The distance light travels in 1 year. Even describing it that way doesn't fully land. The scale remains distant, almost intentionally difficult to imagine. But what matters more than the number is what it implies. There may be galaxies beyond the observable universe, possibly far beyond, so far that their light simply hasn't arrived yet. And in that sense, the universe could be vastly larger than what we will ever be able to observe, even in principle. This reframes the original question. When we ask whether space ends, we are often unknowingly asking whether our observations end. Science tells us those are not the same thing. There could be more universe beyond what we can detect, more structure, more matter, more distance, not hidden behind a wall, but separated by time itself. As the universe continues to age, the observable boundary slowly changes. Some regions that are currently visible will eventually drift beyond our ability to observe, their light stretched and weakened by cosmic expansion. And some regions that are currently invisible may one day come into view. The universe does not present itself all at once. It unfolds gradually. This means the question of whether space ends is not something we can answer simply by looking farther. It requires us to think in terms of models, geometry, and the large-scale behavior of space-time itself. In the next chunk, we'll move beyond observation and into theory, exploring how space can expand without expanding into anything, and how something can be finite without having an edge. As we continue, it helps to slow the question down even further. When scientists talk about whether space ends, they often reframe the question in a quieter, more precise way. What is the shape of the universe? This isn't shape in the everyday sense. Not a silhouette, not an outline. It's a question of geometry. On small scales, space feels flat. If you draw a triangle on a sheet of paper, the angles add up to 180 degrees. On Earth, however, that rule subtly breaks down. If you draw a very large triangle using the surface of the planet, connecting the equator and the poles, the angles add up to more than 180 degrees. That's because Earth's surface is curved. Locally, it feels flat. Globally, it is not. Cosmologists use this same idea. To study the geometry of the universe as a whole, they ask whether space is flat, positively curved like a sphere, or negatively curved like a saddle. Each possibility leads to a very different answer, to the question of whether space ends. If space has positive curvature, the universe could be finite yet unbounded. You could travel in a straight line indefinitely and eventually return to where you started without ever encountering an edge. If space is flat, the universe could be infinite, extending endlessly in every direction. And if space has negative curvature, it could also be infinite, but with distances that grow faster than intuition expects. Measurements of the cosmic microwave background, dash, dash, dash. The faint afterglow of the early universe suggest that space is extremely close to flat, so close that, within our observable region, curvature is almost impossible to detect. But here's the quiet detail that often goes unnoticed. Almost flat does not tell us everything. Our observations are limited to the observable universe. We cannot see far enough to measure the full shape. It's similar to standing on a vast plain. The ground appears flat in every direction, but without traveling far enough, you cannot know whether the land eventually curves. So the universe may be infinite, or it may be finite in a way that hides its boundaries completely. This uncertainty isn't a failure of science. It's a reflection of scale. The universe is so large that even its basic geometry remains partially beyond reach, and there's something calming in that. Not mystery as confusion, but mystery as proportion. The question doesn't remain unanswered because it's too complex. It remains unanswered because the universe is patient and expansive and not required to reveal everything at once. As the universe continues to expand, the observable region may change, but the underlying structure could remain the same. Whether infinite or finite, edge or no edge, space does not behave like a container. It behaves like a relationship between distance, time, and energy. In the next chunk, we'll move even deeper into this idea by exploring what happens when we imagine traveling through the universe forever, and why the idea of an edge may be more about human perspective than cosmic reality. Now that we've talked about expansion and shape, it becomes possible to approach the original question from a different direction. What would happen if you could travel through space forever? Not quickly, not with urgency, just steadily, moving forward without stopping, In everyday life, movement implies destination. A road leads somewhere. A path ends at a boundary. But on cosmic scales, this assumption begins to soften. If space has no edge, then traveling forever does not bring you closer to an ending. It simply brings you somewhere else. Imagine setting out in a single direction, passing stars, then galaxies, then vast regions where galaxies thin out and space grows quieter. You would never encounter a sign that says, "This is the end." No marker, no transition. The laws of physics would remain the same. Distances would stretch, time would continue forward, and the journey itself would not change in character. This idea feels unsettling at first because it conflicts with how the human mind organizes space. We are used to rooms, borders, horizons. We evolved to survive within environments that fit inside vision and memory. But the universe does not share those constraints. If the universe is infinite, traveling forever simply means continuing. There is no outer layer where space stops being space. And if the universe is finite but unbounded, the result is just as strange in a quieter way. You could travel endlessly and eventually return to where you started, not by turning around, but by continuing forward. This is not fantasy. It is a direct consequence of curved geometry. Just as walking straight on Earth eventually leads you back to your starting point, moving straight through a positively curved universe could do the same. No edge required. In both cases, infinite or finite without boundary dash dash. The idea of an end never appears, only continuation. This brings us to an important realization. When people imagine the end of space, they are often imagining a place, a location where something happens differently. But physics does not predict such a place. The equations that describe space-time do not suddenly fail at a distance. They do not suggest a final coordinate where structure dissolves. Instead, they suggest consistency. The same rules apply everywhere we can test them, and every indication we have suggests they would apply just as well beyond what we can observe. This does not mean space must be infinite. It means that ending is not a useful concept at these scales. Even the word edge carries assumptions that do not map well onto reality. Edges belong to objects inside space, not to space itself. A planet has an edge. A star has an edge. A galaxy has an edge. But space is not an object inside something larger. It is the framework in which objects exist. Asking where space ends is a bit like asking where time stops. Time does not suddenly halt at a particular moment. It flows, and space, in the same way, extends. This doesn't require that space be infinite in a literal sense, only that it does not terminate the way physical objects do. There is another quiet implication here. If space does not end, then the universe does not have a preferred direction. No outward, no cosmic north. Every direction is equally valid. Every location equally central from its own point of view. This symmetry is not just philosophical, it appears directly in the mathematics of cosmology. The universe looks roughly the same in every direction. When viewed on the largest scales, not identical dash dash, but statistically uniform. This uniformity is another reason scientists suspect there is no special boundary. Boundaries introduce asymmetry, and the universe, so far as we can measure, does not favor one side over another. So when we imagine traveling forever, we're not imagining an impossible journey. We're imagining a continuation through a structure that does not announce its limits. And perhaps the most calming part of this idea is how little it demands from us. There is no need to picture infinity all at once. No need to grasp the whole. The universe does not require comprehension to exist. It continues quietly, whether observed or not. And when that idea settles for a moment, another possibility begins to surface, one that moves beyond the shape of our universe and asks whether what we call the universe is the whole of space at all. It raises the quiet question of scale once again, whether space itself may extend far beyond our cosmic horizon, and whether the universe we observe could be just one region within something even larger. Not as a dramatic reveal, but as a gentle widening of perspective. When the idea of endless travel settles for a moment, another layer quietly comes into view. Up to now, everything we've talked about has taken place within the universe. Its expansion, its shape, its geometry, and the limits of what we can observe. But modern cosmology allows for a more expansive possibility. What if the universe we observe is not the entirety of space? What if it is only a region? A vast one, yes, but still only a portion of something larger? To approach this idea carefully, we need to distinguish between two concepts that sound similar, but mean very different things: the universe and space itself. In everyday language, these words blur together, but in cosmology, they are not always interchangeable. The universe is often defined as everything that has been causally connected since the beginning of cosmic expansion. Everything that shares a common origin in what we call the Big Bang. Space, however, may be more general than that. Some models suggest that space could exist beyond our universe, unchanged by our local expansion history, containing regions that are forever disconnected from us, not far away in distance, but separated by conditions of time, energy, or expansion. This is not science fiction. It emerges naturally from the mathematics used to describe the early universe. According to inflationary theory, the universe underwent an extraordinarily rapid expansion in its earliest moments, so rapid that tiny regions of space we're stretched into enormous cosmic domains. In some versions of this theory, inflation does not happen once and stop. It continues. Different regions of space stop inflating at different times, forming what we experience as individual universes. Our universe would be one such region, a bubble of slower expansion, within a much larger, still inflating background. This background is sometimes referred to as a larger space-time, or an inflationary space. Within it, our universe is not central. It is not unique. It is simply one outcome among many. Each region could have different physical properties, different particle behaviors, different constants, different structures. This idea is often grouped under the term multiverse, though that word carries more weight than is strictly necessary. At its core, the idea is quiet and structural. Space may be far larger than the universe we inhabit, and our universe may not mark the beginning or end of anything, only a particular configuration within a broader framework. What's important here is not whether this idea is ultimately correct. Science does not require belief. It requires consistency with observation and mathematics. What matters is that modern physics allows for this possibility without breaking its own rules. And once allowed, the original question changes again. If space exists beyond our universe, then asking whether space ends becomes even less about edges and more about scope. The universe may have a beginning in time. Space may not. The universe may have a specific history. Space may be more general than history. In this view, space is not something that belongs to the universe. The universe belongs to space. This does not mean space is infinite in a simple sense. It means that its extent is not defined by our local cosmic story. And this perspective does something subtle to the mind. It removes the pressure to locate an ending. The question stops being, where does it stop? And becomes, how large is the framework that allows it at all? And that question does not demand an answer. It invites scale. It invites patience. Even within our own universe, we already live inside limits of knowledge. There are regions we will never observe, events we will never witness, distances that grow faster than information can travel. And yet, physics remains stable. The equations continue to work. The structure remains coherent. This suggests that reality does not require completeness from our perspective. The universe does not owe us visibility, and space, dash, dash, if it extends beyond our universe, does not owe us access. It simply exists, quietly accommodating structure wherever conditions allow. As this idea settles, it leads naturally toward a final, calmer realization that the question, does space ever end, may not have an answer in the way questions usually do. Not because it is unanswerable, but because it is built from assumptions that don't quite apply. In the next movement of thought, we'll gently step back and look at the question itself, how human intuition shapes it, and why the absence of an ending may be less unsettling than it first appears. Before we go any farther outward, it helps to turn inward for a moment, not away from science, but toward the way the human mind naturally frames questions like this one. Because the question, does space ever end, does not arise in a vacuum. It arises from intuition, from experience, from a lifetime spent inside environments that are limited, enclosed, and finite. Every space we have ever occupied has had an ending. Rooms end at walls, land ends at water, paths end at boundaries, fences or horizons. Even when the horizon moves as we walk toward it, we still understand it as a kind of edge. So when we imagine space, we quietly import these assumptions with us. We picture vastness as a larger version of the familiar, a bigger room, a longer road, a farther horizon, and inevitably, we imagine that somewhere far away, there must be a final boundary. But this expectation does not come from physics. It comes from scale. Human intuition evolved to work well within a narrow range of distances, times, and speeds. It did not evolve to reason naturally about billions of light years, curved geometries, or expanding frameworks. So when the universe fails to present an ending, it feels unsettling, not because it is incoherent, but because it does not align with the mental tools we usually rely on. This is an important distinction. Discomfort does not imply contradiction. It often implies unfamiliarity. In physics, many ideas that once felt deeply counterintuitive are now considered foundational. Time dilation, wave-particle duality, the relativity of simultaneity. Each of these challenged intuition. None of them broke reality. The absence of an edge in space belongs to this same category. It feels wrong only because we are asking the universe to behave like a room. But the universe is not a room. It is not an object inside something larger. It is a structure, a set of relationships between distance, time, and energy. And structures do not always terminate the way objects do. There is another subtle habit at work here. When we ask whether space ends, we often imagine a vantage point outside of it, a place from which the whole can be seen. But physics does not offer such a position. There is no external viewpoint, no place to stand beyond space and look back in. Every observation occurs from within the structure itself. This means the question is not just about space. It is about perspective. We are asking whether something ends from a standpoint that may not exist. Once this is noticed, the question softens again, not into meaninglessness, but into clarity. The universe does not need an ending. To be complete, completeness is not defined by closure. It is defined by consistency. And the universe, as far as we can tell, is remarkably consistent. The same physical laws apply across vast distances. The same patterns emerge again and again. This uniformity suggests that there is no privileged location where rules suddenly change, no special place where space gives way to something else. And if there is no such place, then the idea of an ending loses its footing. This does not mean the universe is infinite in a simplistic way. It means that infinity and finitude are not the most useful categories here. What matters more is whether the structure of space requires boundaries, and everything we know suggests that it does not. At this point, it becomes possible to hold the idea of endless space without tension, not as something overwhelming, but as something quietly neutral. Space extends, time flows, structures form and dissolve. None of this requires an edge, and perhaps that is why, when people reflect on this question in quiet moments, it often brings calm rather than anxiety. The mind stops searching for a wall and instead settles into continuity. In the next stretch of thought, we'll look at how modern physics treats beginnings and endings more generally. Why even the beginning of the universe may not be the kind of beginning we usually imagine, and how that further changes the way we think about space itself. As the idea of endless extension becomes more familiar, another assumption quietly comes into focus: that if something does not end, it must also not have begun. But in physics, beginnings and endings do not always mirror one another. The universe, according to our best current models, has a beginning in time, not a beginning in space, but a beginning of expansion. This distinction matters more than it first appears. The Big Bang is often imagined as an explosion, a point where matter burst outward into empty surroundings. But that image is misleading. The Big Bang was not an explosion in space. It was an expansion of space. Every region expanded. Every distance grew. There was no center where it started, no outer region it expanded into. This means the universe can have a beginning without having an edge. Time may have a starting point, even if space does not. This idea challenges another everyday assumption. We are used to beginnings marking the appearance of objects. A house begins when construction starts. A road begins at an intersection. But space-time does not behave like an object. Its beginning, if it has one, is not a location you could visit. It is a boundary in time, not in space. And even that boundary may not be absolute. Some models suggest that what we call the beginning was not a singular moment, but a transition, a change in how space-time behaved. In these models, time itself may extend further back than the Big Bang, but in a form we do not yet fully understand. The universe we inhabit could be one phase of a larger temporal structure. This again shifts the question of endings. If time can have a beginning without implying an edge in space, then the absence of an ending becomes easier to accept. Beginnings and endings are not symmetrical in cosmology. They arise from conditions, not from borders. The early universe was dense, hot, and uniform. As it expanded, structure emerged, galaxies formed, stars ignited, planets assembled. All of this occurred within a framework that did not need walls to hold it together. And as expansion continues, that framework remains intact. Space stretches, distances increase, but the underlying geometry persists. There is no indication that space wears out or thins into nothing. Even the concept of nothing turns out to be unstable in physics. What we call empty space is filled with activity. Quantum fields fluctuate, particles appear and vanish, energy ripples through regions that appear calm. So when we ask whether space ends, we are also asking whether this activity stops, whether the structure that allows physics to operate simply ceases. And once again, there is no evidence that it does. Physics allows for limits, but not abrupt disappearances. What we see instead are transitions, changes in state, changes in behavior, shifts in scale, not endings. This reframing brings the question into a quieter place. Space does not need to end to make sense. Time does not need to stop to be meaningful. The universe does not need closure to be complete. It simply unfolds according to its structure. And that structure, as far as we can tell, does not privilege finality. As this idea settles, one final layer remains. If space does not end, and if beginnings are not what we usually imagine, what does it mean to exist within such a universe? How does this perspective change the way we understand our place? Not in a philosophical sense, but in a physical one. That is where we'll gently turn next. When the question of endings finally loosens its grip, another realization begins to take shape. That regardless of whether space is infinite or finite, without boundary, we already live inside it completely. There is no partial experience of the universe, no outside reference point. Every observation, every measurement, every theory is formed from within the same structure we are trying to understand. This is not a limitation. It is a defining feature of cosmology. We do not study the universe the way we study an object on a table. We study it the way a pattern studies itself, by noticing consistency, variation, and relationship. From this perspective, the absence of an ending becomes less abstract and more practical. Space does not need to end. For physics to function, it does not need an edge. For stars to form, for galaxies to rotate, for light to travel, everything that matters for structure is already present locally. Gravity operates the same way here as it does billions of light years away. The same physical constants apply. The same equations describe motion, energy, and time. This uniformity is one of the strongest clues we have. about the nature of space. If there were an edge, a true boundary where space stopped, we would expect to see its influence, distortions, asymmetries, directional differences in physical law. But what we observe instead is remarkable sameness, not perfect uniformity. The universe is rich with structure, but statistical consistency on the largest scales. This suggests that space is not organized around a center, a border, or a privileged direction. It is organized around relationships. Distances matter. Energy densities matter. Curvature matters. But location does not. There is no here in the universe. That is more fundamental than any other. And once this is understood, the question of endings recedes even further. Because endings imply importance. They imply significance. But space does not appear to assign meaning that way. It does not highlight boundaries. It does not frame itself for interpretation. It simply allows structure to emerge where conditions permit. In that sense, space is not dramatic. It is permissive. It provides the stage, without drawing attention to itself. Even the most violent events, supernovae, collisions of galaxies, the formation of black holes, occur within the same quiet framework. Space does not react. It accommodates. And over time, it smooths. Expansion gradually increases separation. Dense regions thin. Energy spreads, not toward an end, but toward equilibrium. Far into the future, long after stars stop forming, long after galaxies fade beyond observation, space will still exist. It will be colder, darker, more diffuse, but not absent. Physics does not predict a moment where space itself disappears, only changes in what occurs within it. This again reinforces a subtle but important idea. Space is not a phase. It is not a temporary condition. It is the underlying context in which phases occur, and contexts do not end the way events do. They persist, as long as the rules that define them remain consistent. This does not make space infinite in a way that demands awe. It makes it stable in a way that invites calm. We do not need to picture endless distance to live comfortably inside it. We only need to recognize that there is no boundary pressing inward, no approaching limit, no final edge that changes what it means to exist here, now. As this settles, there is one last turn worth making. Not toward speculation, but toward perspective, toward what questions remain meaningful. Once the idea of an ending is set aside, that is where this exploration gently comes to rest. One of the most important ideas in modern cosmology is also one of the most difficult to visualize. The universe is expanding. This statement is simple to say, but deeply counterintuitive to understand, because expansion in everyday experience always implies movement into something else. A gas expands into a room. A crowd expands into a street. A ripple expands across the surface of water. In every familiar case, there is space, already there, dash, dash, waiting to be filled. But the expansion of the universe does not work this way. The universe is not expanding into space. Space itself is expanding. This distinction is subtle, and it changes how we think about endings entirely. When astronomers observe distant galaxies, they notice something consistent. The farther away a galaxy is, the farther away it is, the faster it appears to be moving away from us. At first glance, this might seem to place us at the center of everything. But when scientists examine the data carefully, a different picture emerges. Every galaxy sees the same thing. From any location in the universe, other galaxies appear to be moving away. There is no central point of expansion, no privileged location. This is one of the clearest indications that it is space itself that is stretching. To understand this more gently, it helps to return to analogy, dash, dash, not as explanation, but as orientation. Imagine the surface of a balloon, not the air inside, only the surface. If dots are drawn on that surface, and the balloon is slowly inflated, each dot moves away from every other dot. No dot is the center. No dot moves through the surface faster than another. The surface itself grows. From the perspective of any dot, all the others recede. And importantly, the surface has no edge. You could travel in any direction along that surface without ever encountering a boundary. Yet the surface is finite. It has an area. It has geometry. This is not how we usually think about space. We expect finiteness to imply borders. We expect extension to imply direction. But geometry allows other possibilities. In cosmology, this analogy helps us understand how space can expand without expanding into anything. There is no outside reference frame, no surrounding emptiness. The universe is not embedded in something larger. In the way objects are embedded in rooms, it is self-contained, and this self-contained expansion is one of the strongest reasons. Scientists hesitate to talk about an edge. An edge would imply something beyond it, a transition into a different kind of space. But expansion does not point toward such a transition. It is uniform. It is internal. It is everywhere. As space expands, distances between objects increase. But the objects themselves, galaxies, stars, atoms, are not stretching in the same way. Local structures remain intact. Gravity, electromagnetic forces, and atomic bonds hold matter together on smaller scales. This is why galaxies do not dissolve as the universe expands, why solar systems remain stable, why everyday distances do not grow. Expansion matters only across vast, intergalactic scales. This selective effect is another clue about the nature of space. It is not something that behaves like a material substance. It does not pull or tear indiscriminately. It responds to scale, and over large enough distances, its expansion becomes dominant. As expansion continues, something else happens, quietly, steadily. Light traveling through space is stretched along with it. Wavelengths grow longer. Energy spreads thinner. This is why distant galaxies appear redder over time, their light shifted toward longer wavelengths. This phenomenon, cosmological redshift, is not caused by motion through space alone, but by the stretching of space itself. And this stretching has consequences. There are regions of the universe so distant that the space between us and them is expanding faster than light can cross it. This does not violate relativity. Nothing is moving through space faster than light. Space itself is changing, and this creates a kind of horizon. Not a wall, not an ending, but a limit to communication. Some regions are already beyond our ability to ever observe. Their light will never reach us. Not now, not in the future. They exist, they evolve, but they remain forever disconnected. This idea is sometimes unsettling because it suggests that knowledge itself has limits, but those limits are not imposed by barriers. They arise naturally from the structure of space-time. And once again, the notion of an edge becomes unnecessary. Space does not need to stop. In order for horizons to exist, it only needs to expand. As expansion continues, indefinitely the observable universe changes shape. Some galaxies drift beyond visibility. Others fade as their light stretches thinner. But space itself remains, not thinning, not weakening, simply continuing. And here, the question transforms yet again. If space can expand without an edge, if distance can increase without pointing outward, if regions can become unreachable without boundaries, then what does it even mean to ask where space ends? The question assumes a direction that may not exist. It assumes that space behaves like a region inside something else. But expansion tells a different story. Space is not contained. It is the container, and containers do not require edges when they are the totality of what exists. This realization does not demand awe or overwhelm. It invites patience. The universe is not rushing toward an ending. It is not unfolding toward a boundary. It is stretching, calmly, evenly, according to rules that apply everywhere at once. And when viewed this way, endlessness is not dramatic. It is neutral. It is simply what follows when geometry and time interact on scales far larger than intuition evolved to handle. As this expanded idea settles, the earlier question begins to soften, not into insignificance, but into clarity. Space may not end because it does not need to. It does not function like something that ends. It functions like something that continues, and that continuation, quiet and structure-bound, sets the stage for everything else the universe does. Once the idea of expansion settles into place, another consequence begins to emerge. Not abruptly, but gradually. The universe does not only grow larger, it also grows quieter. Not in the sense of silence, but in the sense of separation. As space expands, distances between regions increase, and with those increasing distances come natural limits on what can be known, seen, or shared. This is where the concept of a cosmic horizon becomes important. In everyday life, a horizon feels like an edge, the place where land meets sky, a boundary beyond which details disappear. But a cosmic horizon is not an edge of space. It is an edge of information. It marks the furthest distance from which signals, light, gravity, any form of influence, can reach an observer within a given amount of time. This distinction matters. Nothing special happens at a cosmic horizon. No wall exists there. No physical change takes place. The laws of physics remain the same on both sides. The horizon is defined entirely by timing. Light has not had enough time to cross the expanding distances. And because expansion continues, some regions will never be able to communicate with us at all. This means the universe naturally sorts itself into what is knowable and what is not because of obstruction, but because of structure. In this way, ignorance is not a failure of observation. It is a built-in feature of space-time. As the universe ages, these horizons evolve. Early in cosmic history, everything was closer together. Regions that are unreachable now were once near enough to interact. As expansion accelerated, those connections stretched and thinned until they quietly broke. Not in a dramatic event, but in a slow drifting apart. This gradual loss of connection is one of the most profound outcomes of expansion. Entire galaxies can slip beyond our horizon without ever changing in themselves. They continue forming stars. They continue evolving. They simply do so beyond our reach. And this has an important implication for the question of endings. If regions of space can become permanently inaccessible, without space itself ending, then endings are not required. To create limits, limits arise naturally from distance and time. This again undermines the idea that space must terminate somewhere. Space does not need to stop for there to be boundaries of experience. Those boundaries emerge on their own. There is another quiet effect of distance worth noticing. As space expands, it does not expand evenly in terms of perception. Nearby structures remain visible and coherent. Distant ones fade. Light weakens. Details blur. Eventually, only the closest structures remain observable. Far in the future, an observer inside a galaxy like ours may see only their own local group of galaxies. Everything else will have drifted beyond the cosmic horizon. To that observer, The universe may appear small and isolated, not because space has ended, but because expansion has removed access. This imagined future highlights something subtle. The appearance of the universe depends on when and where you observe it. Space does not present itself the same way at all times, and this time dependence further complicates the idea of an ending. An ending suggests permanence, a final state, but cosmic horizons are dynamic. They move, they change. What is observable now was not always observable and will not always remain so. This means that even our current picture of the universe is temporary, not incorrect, but incomplete. And incompleteness, again, does not imply termination. It implies process. The universe is not arranged to be fully revealed. It unfolds according to rules that allow structure but do not guarantee access. And perhaps this is one of the most calming realizations. Hidden inside the science, we are not meant to see everything. The universe does not expect comprehension. It simply continues. Space expands. Horizons form. Connections stretch and fade. None of this requires an edge. None of this points toward an ending. It points toward continuity, with changing conditions. And within those conditions, knowledge finds its place. Limited, local, and sufficient. As this understanding settles, one more question naturally rises. If the universe imposes limits on what can be known, and if space extends without obvious boundaries, what does it mean to talk about everything at all? What does totality mean? In a universe where access is finite, but structure is not, that quiet question is where we'll turn next, letting it unfold slowly, without forcing resolution, as horizons and distance reshape what can be known. The idea of everything begins to feel less solid. In everyday language, everything sounds complete. It suggests a total collection, dash dash. All objects gathered, all facts accounted for. But in cosmology, everything is not something we can point to. It is something we infer. What we call the universe is not defined by total access, but by shared history. It is the region of space-time that has been causally connected, that shares a common expansion story, a common physical framework. This is a subtle definition. It does not say that nothing exists beyond it. It says only that beyond it, connection has never occurred, and this distinction quietly reshapes what everything means. Because if connection defines inclusion, then separation defines exclusion dash dash. Not as absence, but as independence. There may be regions of space that are as real as our own, governed by the same mathematics, yet forever outside our cosmic conversation. They are not hidden behind walls. They are not sealed off by barriers. They are simply too distant in time and expansion to ever interact. This means that totality is not something any observer can witness. It is something that exists only as structure, and structure does not require observation to persist. This realization removes another assumption, that to exist is to be observable, but physics does not support this. Most of the universe is already unobservable to us, not because it is small or subtle, but because it is far. Distance alone is enough to separate reality from experience. And this brings us back to the question of endings. When people imagine the end of space, they are often imagining the end of relevance, a place beyond which nothing matters. But relevance is not a physical property, it is a human one. Space does not organize itself around importance or meaning. It organizes itself around relationships, causal connection, interaction, influence. Where those end, experience ends. But space does not. This reframing is important because it allows us to hold two ideas at once, without contradiction. Space can extend beyond all experience, and experience can remain complete within itself. We do not need access to everything for what we know to be coherent. Physics does not collapse because of unseen regions. It remains stable, predictive, and internally consistent. This suggests that the universe is not designed to be fully grasped, not as a puzzle with a final image, but as a process with internal logic. And processes do not need edges, they need rules. As long as those rules remain consistent, the process continues. The universe does not ask to be finished, it asks only to be allowed to unfold. In that sense, space does not end, because ending is not part of its function. It is not a story with a final chapter. It is a framework within which stories occur. Stars form and fade. Galaxies merge and separate. Energy spreads, all within the same quiet backdrop. And that backdrop does not announce its limits. As this idea settles, one final shift becomes possible, not toward a new theory, but toward a simpler stance. What if the question, does space ever end, is less about finding an answer and more about recognizing the scale at which answers stop being necessary? What if continuity itself is enough? That is where this exploration gently moves next, not toward resolution, but toward a calm resting place within the structure we already inhabit. At this point, the question has changed, not in wording, but in weight. Early on, does space ever end, felt like a problem waiting for resolution, a mystery that must eventually yield a clear answer. But after moving through expansion, geometry, horizons, and scale, the question begins to rest differently. It no longer presses forward. It settles, because what has emerged is not an absence of answers, but a shift in what kind of answer makes sense. In physics, endings usually arise from breakdowns. A rule stops working, a structure fails. A process runs out of conditions that allow it to continue. But space shows no sign of this. There is no equation that predicts a place where space-time stops behaving like space-time. No observation that hints at a final layer, beyond which structure dissolves. Instead, every model that successfully describes the universe treats space as something that persists, changing, stretching, curving, but not terminating. And this persistence does not require infinity. It requires only consistency. A universe can be finite without an edge. It can expand without moving outward. It can contain horizons without containing walls. All of these ideas felt unfamiliar at first because they contradict everyday intuition. But familiarity is not the same as truth. Human intuition evolved for survival, not for cosmology. It works beautifully at human scales. It falters at cosmic ones. Once this is accepted, the lack of an ending stops feeling incomplete. It starts to feel appropriate. Space is not a journey with a destination. It is a condition. It allows distances to exist, events to occur, time to move forward, and conditions do not end the way journeys do. They remain in effect, as long as the rules that define them remain valid. So far, nothing we have observed suggests those rules are approaching failure. The universe is not running out of space. It is not approaching a boundary. It is continuing, not toward something, but according to itself. This does not make the universe cold or indifferent. It makes it stable, predictable where it needs to be, open-ended where it can be. And perhaps this is why, when the question is allowed to fully unfold, it often leads to calm rather than unease. There is no looming edge to worry about, no final wall waiting in the distance, just structure continuing, at scales far beyond immediate concern. The universe does not rush toward closure. It unfolds patiently, and within that unfolding, there is room for everything that happens locally. Stars, forming planets circling, observers wondering. None of this depends on space ending. It depends only on space existing, and that existence, as far as science can tell, does not come with an expiration point. So the question rests, not because it has been answered definitively, but because it no longer demands urgency. Space may be infinite. It may be finite without boundary. It may be larger than the universe we observe. Each of these possibilities fits within what we know. None require an ending. And perhaps that is the quiet conclusion. That space does not need to end for the universe to make sense. Continuity is not a problem to solve. It is a condition to recognize. And with that recognition, the mind no longer searches for a final edge. It simply remains within a universe that does the same. As the idea of an ending slowly fades from view, another understanding begins to take its place. That continuity is not an exception in physics. It is the default. When scientists model the universe, they do not begin by asking where it stops. They begin by asking how it behaves. They look for relationships that hold across distance, patterns that repeat across scale, rules that remain valid regardless of location. And what they consistently find is not evidence of termination, but evidence of persistence. Space behaves the same way here as it does billions of light years away. Time flows forward without preference. Physical laws do not weaken with distance. Geometry does not fray at the edges. In fact, nothing in our observations suggests that space is approaching a condition where it would need to stop. Even dramatic changes in the universe, the formation of structure, the acceleration of expansion, the eventual fading of stars, dash, dash, all occur within a framework that remains intact. Space accommodates these changes. It does not collapse under them. This is an important distinction. Endings usually arise from exhaustion. A process runs out of energy. A system reaches instability. A structure fails under strain. But space does not behave like a consumable resource. It is not used up by expansion. It is not worn down by time. Expansion does not thin space into nothing. It stretches relationships between points. And stretching, in physics, is not the same as depletion. As distances increase, space remains fully present at every location. There is no evidence of tearing, no sign of fragility. This suggests that space is not something that exists within the universe. It is something the universe exists within. And that subtle reversal matters, because if space were a thing among other things, it might reasonably have boundaries. But if space is the condition that allows things to exist at all, then boundaries become unnecessary. Conditions do not end the way objects do. They persist, as long as the rules that define them remain coherent. Another way to see this is to consider how physics treats extremes. At the smallest scales, quantum mechanics describes a restless, fluctuating reality. At the largest scales, general relativity describes smooth, continuous spacetime. These two descriptions are very different and not yet fully unified, but neither suggests a breakdown of space itself. Even where our theories struggle, they struggle with description, not with existence. Uncertainty does not mean absence. It means our models are incomplete. And incompleteness, again, does not imply an ending. It implies room for refinement. This is one of the quieter strengths of science. When it encounters limits, it does not assume reality stops there. It assumes understanding does. The universe continues, even when our explanations do not. And this attitude reflects something important about the question we started with. Asking whether space ends assumes that the universe must conform to a human sense of completion, but physics does not operate under narrative constraints. It does not require a final chapter. It does not build toward closure. It unfolds according to structure, and structure, once established, tends to persist. This persistence is not dramatic. It does not announce itself. It simply remains in effect. Space does not draw attention to its continuity, because continuity is unremarkable at cosmic scales. It is expected. What changes are the contents. Stars ignite and burn out. Galaxies collide and merge. Energy spreads and cools. But the framework that allows these changes remains stable, even in far future scenarios where the universe becomes dark and dilutes. Space itself does not vanish. It becomes quieter, less structured, but still present. This means that worrying about the end of space is a bit like worrying about the end of distance itself. Distance may become less relevant in some contexts, but it does not cease to exist. Time may stretch or slow, but it does not simply stop. Space belongs to this same category. It is not an event, it is a condition, and conditions do not seek resolution. They remain until something replaces them. So far, nothing we know suggests there is anything waiting to replace space. No alternate framework pressing in. No external structure preparing to take over. Only continuity. And continuity, when viewed without urgency, can be surprisingly calming. It removes the need to anticipate an end. It removes the pressure to imagine a final boundary. The universe is not moving toward disappearance. It is moving through change within a stable framework. As this realization settles, the mind can finally let go of the original tension. The question no longer pulls forward. It rests, and in that resting, there is one final perspective worth considering. Not about what space does or how it behaves, but about how questions themselves change when continuity is allowed to be enough. That is where this exploration will gently come to a close. By now, the question that opened this exploration has changed in character. It hasn't been answered in the way questions often are, with a clear boundary, a defined endpoint, a statement that closes the matter. Instead, it has softened. Does space ever end? No longer feels like something that needs resolution. It feels like something that has found its place. This shift is subtle but important. In science, some questions persist, not because they lack answers, but because they reveal the limits of how questions are formed. They point less toward facts and more toward perspective. This question does exactly that. Early on, it seemed to ask about distance, about how far space extends, about whether there is a final region beyond which nothing exists. But as the structure of space-time comes into view, it becomes clear that distance alone is not the heart of the matter. Space is not arranged to culminate. It is arranged to relate. It connects events. It allows separation and proximity. It provides a framework within which time unfolds. And once those roles are understood, the idea of an ending begins to feel unnecessary. Space does not behave like a story with a final page. It behaves like a condition that remains in effect. Even the most dramatic changes in the universe do not bring it closer to stopping. Expansion does not exhaust it. Cooling does not erase it. Darkness does not undo it. These are changes in contents, not changes in context. This distinction matters because contexts do not need closure to remain meaningful. They simply continue until replaced by something else. And so far, there is no evidence that anything is waiting to replace space. No external structure pressing inward. No alternate framework approaching. Only the same quiet geometry, holding distance and time together. This does not mean the universe is static. Far from it. Change is constant. But change occurs within continuity, not toward its elimination. This is why the universe can evolve without approaching a final edge. It is not moving toward disappearance. It is moving through variation. Stars will eventually stop forming. Galaxies will drift farther apart. Energy will spread thinner. But none of these imply that space itself ends. They imply that structure becomes simpler, more diffuse, less concentrated. The framework remains. And perhaps this is where the original question finds its quiet resolution. Not in certainty, but in stability. Space does not need an end to make sense of existence within it. It does not need a boundary. To support structure, it does not need a final answer. To remain coherent, it simply needs to persist. And persistence, as far as physics can tell, is exactly what it does. This perspective does something gentle to the mind. It removes urgency. There is no approaching limit to anticipate, no final wall to imagine, only continuity extending beyond concern. The universe does not demand comprehension. It does not wait for closure. It exists according to rules that allow complexity locally and simplicity globally. And within those rules, questions rise, change shape, and sometimes settle without being resolved. This is not a failure of understanding. It is a feature of scale. Some questions are meant to open perspective, not close it. They guide attention outward, then allow it to rest. Does space ever end? Is one of those questions. Not because it lacks meaning, but because its meaning changes as understanding deepens. And once that change occurs, the question no longer presses forward. It remains quietly in the background, no longer asking for an edge, no longer searching for a boundary, simply existing within a universe that does the same. And in that quiet persistence, there is nothing left to resolve.